Unix time is a system for describing instants in time, defined as the number of seconds that have elapsed since 0 o'clock Coordinated Universal Time, Thursday 1 January 1970, not counting leap seconds. It is used widely in Unix-like and many other operating systems and file formats. Due to its handling of leap seconds, it is neither a linear representation of time nor a true representation of UTC. Unix time may be checked on most Unix systems by typing date plus %s on the command line. Definition: 2 layers of encoding make up Unix time. These can usefully be separated. The first layer encodes a point in time as a scalar real number, and the second encodes that number as a sequence of bits or decimal digits. As is standard with UTC, this article labels days using the Gregorian calendar, and counts times within each day in hours, minutes, and seconds. Some of the examples also show International Atomic Time, another time scheme, which uses the same seconds and is displayed in the same format as UTC, but in which every day is exactly 86,400 seconds long, gradually losing synchronization with the Earth's rotation at a rate of roughly 1 second per year. Encoding time as a number, Unix time is a single-signed integer number which increments every second, without requiring the calculations to determine year, month, day of month, hour and minute required for intelligibility to humans. Modern Unix time is based on UTC, which counts time using SI seconds, and breaks up the span of time into days almost always 86,400 seconds long, but due to leap seconds occasionally 86,401 seconds. This extra second keeps the days synchronized with the rotation of the Earth, per universal time. The Unix epoch is the time 0 o'clock UTC on January 1, 1970. There is a problem with this definition, in that UTC did not exist in its current form until 1972. This issue is discussed below. For brevity, the remainder of this section uses ISO 8601 date format, in which the Unix epoch is 1970-01-01T00000Z. The Unix time number is 0 at the Unix epoch, and increases by exactly 86,400 per day since the epoch. Thus 2004-09-16T00000Z, 12,677 days after the epoch, is represented by the Unix time number 12,677 or 86,400 equals 1,095,292,800. This can be extended backwards from the epoch too, using negative numbers. Thus 1957-10-04T00000Z, 4472 days before the epoch, is represented by the Unix time number -4472 or 86,400 equals -386,380,800. Within each day, the Unix time number is as calculated in the preceding paragraph at midnight UTC, and increases by exactly 1 per second since midnight. Thus 2004-09-16T1755-43.54Z, 64,543.54s since midnight on the day in the example above, is represented by the Unix time number 1,095,292,800 plus 64,543.54 equals 1,095,357,343.54. On dates before the epoch the number still increases, thus becoming less negative, as time moves forward. Leap seconds, the above scheme means that on a normal UTC day, of duration 86,400 seconds, the Unix time number changes in a continuous manner across midnight. For example, at the end of the day used in the examples above, the time representations progress as follows: when a leap second occurs, so that the UTC day is not exactly 86,400 seconds long, a discontinuity occurs in the Unix time number. The Unix time number increases by exactly 86,400 each day, regardless of how long the day is. When a leap second is deleted, the Unix time number jumps up by 1 where the leap second was deleted, which is the end of the day. When a leap second is inserted, the Unix time number increases continuously during the leap second, during which time it is more than 86,400 seconds since the start of the current day, and then jumps back by 1 at the end of the leap second, which is the start of the next day. For example, this is what happened on strictly conforming POSIX1 systems at the end of 1998. Observe that when a positive leap second occurs, the Unix time numbers repeat themselves. The Unix time number 915,148,800.50 is ambiguous. It can refer either to the instant in the middle of the leap second, or to the instant 1 second later, half a second after midnight UTC. In the theoretical case when a negative leap second occurs, no ambiguity is caused, but instead there is a range of Unix time numbers that do not refer to any point in time at all. A Unix clock is often implemented with a different type of positive leap second handling associated with the network time protocol. This yields a system that does not conform to the POSIX standard. See the section below concerning NTP for details. When dealing with periods that do not encompass a UTC leap second, the difference between two Unix time numbers is equal to the duration in seconds of the period between the corresponding points in time. This is a common computational technique. However, where leap seconds occur, such calculations give the wrong answer. In applications where this level of accuracy is required, it is necessary to consult a table of leap seconds when dealing with Unix times, and it is often preferable to use a different time encoding that does not suffer this problem. A Unix time number is easily converted back into UTC by taking the quotient and modulus of the Unix time number, modulo 86,400. The quotient is the number of days since the epoch, and the modulus is the number of seconds since midnight UTC on that day. If given a Unix time number that is ambiguous due to a positive leap second, this algorithm interprets it as the time just after midnight. It never generates a time that is during a leap second. If given a Unix time number that is invalid due to a negative leap second, it generates an equally invalid UTC time. If these conditions are significant, it is necessary to consult a table of leap seconds to detect them. Non-synchronous network time protocol-based variant, commonly a Mills-style Unix clock, is implemented with leap second handling not synchronous with the change of the Unix time number. The time number initially decreases where a leap should have occurred, and then it leaps to the correct time 1 second after the leap. This makes implementation easier, and is described by Mills' paper. This is what happens across a positive leap second. This can be decoded properly by paying attention to the leap second state variable, which unambiguously indicates whether the leap has been performed yet. The state variable change is synchronous with the leap. A similar situation arises with a negative leap second, where the second that is skipped is slightly too late. Very briefly, the system shows a nominally impossible time number, but this can be detected by the time-del state and corrected. In this type of system, the Unix time number violates POSIX around both types of leap second. Collecting the leap second state variable along with the time number allows for unambiguous decoding, so the correct POSIX time number can be generated if desired, or the full UTC time can be stored in a more suitable format. The decoding logic required to cope with this style of Unix clock would also correctly decode a hypothetical POSIX conforming clock using the same interface. This would be achieved by indicating the time INS state during the entirety of an inserted leap second, then indicating time wait during the entirety of the following second while repeating the seconds count. This requires synchronous leap second handling. This is probably the best way to express UTC time in Unix clock form, via a Unix interface, when the underlying clock is fundamentally untroubled by leap seconds. TAI-based variant, another, much rarer, non-conforming variant of Unix timekeeping, involves encoding TAI rather than UTC. Some Linux systems are configured this way. Because TAI has no leap seconds, and every TAI day is exactly 86,400 seconds long, this encoding is actually a pure linear count of seconds elapsed since 1970-01-01 T00000 TAI. This makes time interval arithmetic much easier. time values from these systems do not suffer the ambiguity that strictly conforming POSIX systems or NTP-driven systems have. In these systems it is necessary to consult a table of leap seconds to correctly convert between UTC and the pseudo-Unix time representation. This resembles the manner in which time zone tables must be consulted to convert to and from civil time. The IANA time zone database includes leap second information, and the sample code available from the same source uses that information to convert between TAI-based timestamps and local time. The leap second table must be updated more frequently than the time zone tables, because leap seconds occur at shorter notice than changes to daylight saving time rules. Conversion also runs into definitional problems prior to the 1972 commencement of the current form of UTC. This TAI-based system, despite its superficial resemblance, is not Unix time. It encodes times with values that differ by several seconds from the POSIX time values, and does not have the simple mathematical relationship to UTC that is mandated by POSIX, representing the number. A Unix time number can be represented in any form capable of representing numbers. In some applications the number is simply represented textually as a string of decimal digits, raising only trivial additional problems. However, certain binary representations of Unix times are particularly significant. The standard Unix time T is assigned integer data type, traditionally of 32 bits, directly encoding the Unix time number as described in the preceding section. Being 32 bits means that it covers a range of about 136 years in total. The minimum representable time is December 13, 1901, and the maximum representable time is January 19, 2038. The second after 3:14 and 7 seconds UTC January 19, 2038 this representation overflows. This milestone is anticipated with a mixture of amusement and dread. See year 2038 problem. In some newer operating systems, time T has been widened to 64 bits. In the negative direction, this goes back more than 20 times the age of the universe, and in the positive direction for approximately 293 billion years. There was originally some controversy over whether the Unix time T should be signed or unsigned. If unsigned, its range in the future would be doubled, postponing the 32-bit overflow. However, it would then be incapable of representing times prior to 1970. The consensus is for time T to be signed, and this is the usual practice. The software development platform for version 6 of the QNX operating system has an unsigned 32-bit time T, though older releases used a signed type. The POSIX and Open Group Unix specifications include the C standard library, which includes the time types and functions defined in the time H header file. The ISO-C standard states the time T must be an arithmetic type, but does not mandate any specific type or encoding for it. Unix has no tradition of directly representing non-integer Unix time numbers as binary fractions. Instead, times with sub-second precision are represented using composite data types that consist of two integers, the first being a time T, and the second being the fractional part of the time number in millionths or billionths. These structures provide a decimal-based fixed-point data format, which is useful for some applications, and trivial to convert for others. UTC basis, the present form of UTC, with leap seconds, is defined only from January 1, 1972 onwards. Prior to that, since January 1, 1961 there was an older form of UTC in which not only were there occasional time steps, which were by non-integer numbers of seconds, but also the UTC second was slightly longer than the SI second, and periodically changed to continuously approximate the Earth's rotation. Prior to 1961 there was no UTC, and prior to 1958 there was no widespread atomic timekeeping. In these eras, some approximation of GMT was used instead of an atomic time scale. The precise definition of Unix time as an encoding of UTC is only uncontroversial when applied to the present form of UTC. Fortunately, the fact that the Unix epoch predates the start of this form of UTC does not affect its use in this era, The number of days from January 1, 1970 to January 1, 1972 is not in question, and the number of days is all that is significant to Unix time. The meaning of Unix time values below +63A072A000 is not precisely defined. The basis of such Unix times is best understood to be an unspecified approximation of GMT. Computers of that era rarely had clocks set sufficiently accurately to provide meaningful sub-second timestamps in any case. Unix time is not a suitable way to represent times prior to 1972 in applications requiring sub-second precision. Such applications must, at least, define which form of UT or GMT they use. As of 2009, the possibility of ending the use of leap seconds in civil time is being considered. A likely means to execute this change is to define a new time scale, called International Time, that initially matches UTC but thereafter has no leap seconds, thus remaining at a constant offset from TAI. If this happens, it is likely that Unix time will be prospectively defined in terms of this new time scale, instead of UTC. Uncertainty about whether this will occur makes prospective Unix time no less predictable than it already is. If UTC was simply to have no further leap seconds, the result would be the same. History: the earliest versions of Unix time had a 32-bit integer incrementing at a rate of 60 Hz, which was the rate of the system clock on the hardware of the early Unix systems. The value 60 Hz still appears in some software interfaces as a result. The epoch also differed from the current value. The first edition Unix Programmer's Manual dated November 3, 1971 defines the Unix time as the time since 0 o'clock, January 1, 1971, measured in 60ths of a second. The user manual also commented that the chronologically minded user will note the 232 60ths of a second is only about 2.5 years. Because of this limited range, the epoch was redefined more than once, before the rate was changed to 1 Hz and the epoch was set to its present value. This yielded a range in excess of 130 years, though with more than half the range in the past. As indicated by the definition quoted above, the Unix timescale was originally intended to be a simple linear representation of time elapsed since an epoch. However, there was no consideration of the details of timescales, and it was implicitly assumed that there was a simple linear timescale already available and agreed upon. Indeed, the first edition manual's definition doesn't even specify which time zone is used. Several later problems, including the complexity of the present definition, result from Unix time having been defined gradually by usage rather than fully defined from the outset. When POSIX1 was written, the question arose of how to precisely define time t in the face of leap seconds. The POSIX committee considered whether Unix time should remain, as intended, a linear count of seconds since the epoch, at the expense of complexity in conversions with civil time, or a representation of civil time, at the expense of inconsistency around leap seconds. Computer clocks of the era were not sufficiently precisely set to form a precedent one way or the other. The POSIX committee was swayed by arguments against complexity in the library functions, and firmly defined the Unix time in a simple manner in terms of the elements of UTC time. Unfortunately, this definition was so simple that it didn't even encompass the entire leap year rule of the Gregorian calendar, and would make 2100 a leap year. The 2001 edition of POSIX1 rectified the faulty leap year rule in the definition of Unix time, but retained the essential definition of Unix time as an encoding of UTC rather than a linear time scale. Also, since the mid-1990s, computer clocks have been routinely set with sufficient precision for this to matter, and they have most commonly been set using the UTC-based definition of Unix time. This has resulted in considerable complexity in Unix implementations, and in the network time protocol, to execute steps in the Unix time number whenever leap seconds occur. Notable events in Unix time: Unix enthusiasts have a history of holding time tea parties to celebrate significant values of the Unix time number. These are directly analogous to the New Year celebrations that occur at the change of year in many calendars. As the use of Unix time has spread, so has the practice of celebrating its milestones. Usually it is time values that are round numbers in decimal that are celebrated, following the Unix convention of viewing time t values in decimal. Among some groups round binary numbers are also celebrated, such as plus 230 which occurred at 13:37 and 4 seconds UTC on January 10, 2004. The events that these celebrate are typically described as n seconds since the Unix epoch, but this is inaccurate. As discussed above, due to the handling of leap seconds in Unix time, the number of seconds elapsed since the Unix epoch is slightly greater than the Unix time number for times later than the epoch. At 1:46 and 40 seconds UTC on September 9, 2001, the Unix millennium was celebrated. Some programs which stored timestamps using a text representation encountered sorting errors, as in a text sort times after the turnover, starting with a 1-digit, erroneously sorted before earlier times starting with a 9-digit. Affected programs included the popular Usenet reader node and email client Gmail, part of the KDE desktop environment. Such bugs were generally cosmetic in nature and quickly fixed once problems became apparent. The problem also affected many Filtrix document format filters provided with Linux versions of WordPerfect. A patch was created by the user community to solve this problem, since Coral no longer sold or supported that version of the program. The name Millennium is a portmanteau of billion and millennium. At 23:31 and 30 seconds UTC on February 13, 2009, the decimal representation of Unix time reached 1,234,567,890 seconds. In some parts of the world, this day fell on Friday the 13th in the Gregorian calendar. Google celebrated this with the Google Doodle. Parties and other celebrations were held around the world, among various technical subcultures, to celebrate the 1,234,567,890th second. January 26, 2011 was the 15,000th day of Unix time. This was celebrated in Bloomington, Indiana. At 16:53 and 20 seconds UTC on May 13, 2014, the Unix time value 1,400,000,000 seconds was celebrated over the web. At 6:28 and 16 seconds UTC on February 7, 2036, Network Time Protocol will loop over to the next epoch, as the 32-bit timestamp value used in NTP will overflow. At 3:14 and 8 seconds UTC on January 19, 2038, 32-bit versions of the Unix timestamp will cease to work, as it will overflow the largest value that can be held in a signed 32-bit number. Before this moment, software using 32-bit timestamps will need to adopt a new convention for timestamps, and file formats using 32-bit timestamps will need to be changed to support larger timestamps or a different epoch. At 6:28 and 15 seconds UTC on Sunday 7 February 2106, the Unix time will reach FFFFFFFF16 or 4,294,967,295 seconds which, for systems that hold the time on 32-bit unsigned numbers, is the maximum attainable. For these systems, the next second will be incorrectly interpreted as 0:01 January 1970 UTC. At 15:30 and 8 seconds UTC on Sunday 4 December 292, 277,026,596 64-bit versions of the Unix timestamp will cease to work, as it will overflow the largest value that can be held in a signed 64-bit number. This is not anticipated to pose a problem, as this is considerably longer than the time it would take the Sun to theoretically expand to a red giant and swallow the Earth. In literature and calendrics, Werner Vinge's novel, A Deepness in the Sky, describes a spacefaring trading civilization tens of thousands of years in the future that apparently still uses the Unix epoch. The programmer archaeologist responsible for finding and maintaining usable code in mature computer systems first believes that the epoch refers to the time when man first walked on the moon, but then realizes that it is the 0 second of one of humankind unregistered trademark S first computer operating systems. The Unix epoch features prominently in the construction of the Terang computational calendar. Notes. See also, System time, Timeline of the far future, Epoch. References. External links.